Hello, my name is Siddharth, and in this video, I'll be giving a presentation on the work I have done for my final year project, supervised by Prof. Anvitaman Datta. Here's an overview of my presentation. I'll begin by giving a brief introduction of the background and goal of this project. The aim of this project was to achieve atomic read-modify-write ARMW semantics over an erasure-coded distributed storage system in the presence of Byzantine failures. In the upcoming slides, we will quickly cover the background of the relevant technical aspects. The atomic read-modify-write semantics is formally defined as follows. If updates F and G are performed on AT concurrently, the only acceptable sequences of values for AT is AT, F of AT, G of F of AT, or AT, G of AT, F of G of AT. So in the example shown here on the slide, the only acceptable values for A would be 6 or 4. For distributed systems, a Byzantine failure is the failure of a server where it may not just crash, but also start behaving incorrectly and produce unexpected or wrong results. In the example, client A requests to read the value of A from server 1, but server 1 incorrectly returns the value A equals 2. This is a Byzantine failure. This issue can be solved by replication. The client here, in this case, must request the value of A from all the servers and then apply a simple majority logic to determine the correct value of A. An alternative solution to replication is to use erasure coding, which is essentially an extension of the concept of parity. An NK code consists of a pair of linear functions, encode and decode, such that encode takes as input k data points and outputs the original k data points, as well as n minus k additional parity data points, which are together referred to as the encoded data points, while decode takes as input any k of the n encoded data points and outputs the original k data points. We will now move on to review the relevant literature. One of the major challenges introduced by the Byzantine failures is that it is quite difficult to verify the integrity of data, since the data proposed by any server cannot be trusted. To combat this, we utilize a very powerful idea from a paper, which is known as homomorphic fingerprinting. Such a function is essentially a hash function that satisfies a reasonably low threshold of collision and has linear properties. Usually, these fingerprints are much smaller than the data itself that is required to be stored, and hence can be stored with minimal overhead at every server. Using homomorphic fingerprinting, the property shown on the slide can be easily proven. The crucial implication of this mathematical result is that the integrity of a single data point can be verified using just the fingerprints of all the data points without ever having to receive every data point. Granger et al. Made use of this very powerful idea to improve an existing algorithm known as AVID, which reliably disperses information in a distributed storage system, and called their improvement AVID FP. This protocol details the reliable dispersal of data from a client to servers in the system in the presence of Byzantine failures, as well as the reliable read of data from the system in the same setting, but does not detail how updates can be handled. We also utilize the concept of quorums. A quorum is a subset of nodes of a particular minimum size that, if acquired, can guarantee the correctness of the required read or write operation. Taking inspiration from a paper that utilizes quorums to achieve ARMW semantics over crash failures, we also apply this concept for our proposal, the exact details of which will be covered in the methodology section. Another point which we utilize from the same paper is the idea of differential updates to parity blocks in an erasure-coded distributed system. In particular, it suffices to have the latest differential update and the update target to compute the update to any parity data point, thus removing the necessity to perform a full recomputation. We now move on to the methodology section. On this slide, I summarize the overall working of the system when the storage system receives a client request. Depending on whether the request is a read or write operation, the system then goes about granting a read or write quorum, respectively, for the client. Note here the distinct definition of read and write quorums. Then, once the quorum has been acquired, an update propagation protocol brings any out-of-date nodes up to date if need be. Finally, the read or update protocol is executed depending on the type of request, and the final read results or acknowledgement of the write operation is sent back to the client. Note that in the above flowchart, the quorums are acquired by using a distributed locking protocol such as Redis Labs' RedLock algorithm. Such a protocol makes the assumption of a timed asynchronous system, which will be formally defined in the next slide. A timed asynchronous system is one where every server has access to local hardware clocks, and therefore bounds can be defined on processing times for messages. I reiterate here that this assumption is necessitated due to the requirement of a distributed locking mechanism. The quorums for the proposed system are defined as shown in the slide. We denote by F the maximum number of Byzantine failures among the servers, and NK are the code parameters. The design here is inspired by the quorums over codes paper. A read quorum is obtained using shared locks and contains more than half of the parity nodes, thus allowing multiple reads to take place simultaneously. Whereas a write quorum is obtained by using exclusive locks and contains more than half of the parity nodes, thus precluding a simultaneous read and write or two simultaneous writes. Now we will quickly run through the update and update propagation protocols without proofs for the sake of time. A client first acquires a write quorum and computes the fingerprint of the desired updated value. Then it sends an update message to each server in the quorum containing the differential update, updated fingerprint, and target block. Once the server receives the update request, it stores the updated data, fingerprints, and latest differential update. If the data is consistent with the fingerprints, then the updated fingerprint is echoed to all the other servers in the write quorum. Then, whenever a server receives update echo messages with matching fingerprints from Q-F servers, where Q is the size of the quorum, the update is deemed to have concluded, and this matching fingerprint is stored as the verified one. Finally, an acknowledgement is sent to the client. Once the client receives F+1 acknowledgements with matching fingerprints, then it is confirmed that the update will propagate to a sufficient number of nodes. Before a read or write can be carried out, however, the servers must be brought up to date. This is done by having all servers in the quorum send differential update requests to all other servers in the quorum. Then, once a server receives a differential update request from another server in the quorum, it responds with a differential update message, which contains its latest stored fingerprint, latest update target, latest differential update, and latest version. Finally, when a server in the quorum receives differential updates from all the other servers in the quorum, it concludes on the matching latest version, fingerprint, differential update target, and differential update, which has been proposed by at least F+1 servers. We now move on to the simulations and experiments conducted to confirm the validity of the proposed novel model. The following parameters were constant for experiments 1 and 2, the goals of which will be described in the upcoming slides. We fixed the block size to be 54 bytes, averaged the results over 50 trials, and performed the following sequence of operations: disperse data, update server 2, retrieve data, update server 1, and retrieve data once again. Experiment 1 examines the effect of the number of Byzantine failures on the number of messages and quorum sizes. Note that on this slide, data message refers to messages that carry a significant amount of data, such as a differential update or a data point, as opposed to messages that carry minimal data, such as fingerprints, which are referred to as control messages here. Firstly, the columns highlighted in green here demonstrate that as the number of failures increases, the average number of data messages, average quorum size, and average number of update propagation messages also increase. This is expected since the quorum size increases linearly with the number of failures. The number of data messages and update propagation messages are heavily dependent on quorum size. Also note that the number of control messages do not have any direct correlation with the number of failures, since the number of control messages involved is highly dependent on the lock-in mechanism, which can cause a random number of messages to be transmitted in the system. Experiment 2 examines the impact of code parameters on the number of messages and quorum sizes. Here, we see that as the code parameters k and n become larger, the number of data messages, number of control messages, quorum size, and number of update propagation messages all increase. Also, the code rate doesn't seem to have any direct impact on the rest of the observed values. The goal of experiment 3 was to observe the impact of code parameters, number of Byzantine failures, and the write load on the proportion of servers lagging by more than one update. The code parameters tested were 3, 8, 10, 15, 12, 21, and 15, 25, and all possible combinations of number of failures were tested for each of these goals. Also, all the values were averaged over 50 trials, and in this case, only the acquires and releases of the locks had been simulated. For the sake of brevity, we provide the plots of code parameters 10, 15, and 15, 25 only. We see that as the write load increases, as expected, the chance of a server lagging and missing updates increases. Also, we observe that as the number of failures increases, the probability of a correct server lagging decreases. This is due to the fact that a larger number of failures necessitates a larger quorum size, thereby reducing the probability that a server will be excluded in 3 consecutive updates. We now move on to the conclusion. To the best of our knowledge, this is the first work which achieves atomic read, modify, write semantics over an erasure-coded distributed storage system in the presence of Byzantine failures. It also does so requiring a minimum of 3 F+2 servers in the presence of F Byzantine failures. The development of such protocols will find use in distributed database systems where so-called ACID semantics are required to be guaranteed. I provide here the references used for this presentation. That concludes my presentation. Thank you so much for watching.